Hey everyone, and welcome back to the channel. Today we are diving deep into the foundational pillar of system design, databases. They are the unsung heroes that store, manage, and retrieve the massive amounts of data that powers our modern digital world. So whether you are building a simple mobile app or complex distributed system, choosing the right database is crucial for performance, scalability, and overall success. In this comprehensive guide, we are going to explore 15 common types of databases, discuss their unique strength, and when you should consider using them. So buckle up because we have a lot of ground to cover. So let's start by talking about relational databases. Relational databases organize data into one or more tables consisting of rows and columns. Each row is unequally identified by a primary key, and relationships between tables are established through foreign keys. This structured approach allows relational databases to handle large volumes of structured data, enforce strong data integrity through schemas and constraints, and support complex querying using SQL, the structured query language. They also excel at asset transactions, ensuring atomicity, consistency, isolation, and durability. So let's talk about some common uses for relational databases. The first thing, I guess, they can be used in enterprise application, like managing critical businesses data like customer information, inventory, employee records, and financial transactions where data accuracy and relationships are paramount. They are great in e-commerce platforms, handling product catalogs with numerous attributes, managing customers' orders, and processing payments, or requiring complex queries and reliable transaction management. They are great in banking and financial services, managing accounts, processing financial transactions, and storing user data, where asset properties are non negotiable for maintaining the integrity of financial operations. Next, we start to go through the NoSQL realm, and we start with the key value stores. These databases store data as simple key value pairs, offering incredible fast retrieval based on those um, unique keys. They are they are designed for high scalability, availability, and throughput, making them ideal for scenarios where speed is critical and complex relationships aren't the primary concern. The common use of this one, you can use them in session storage, for example, managing user session information in web application, such as user preferences, shopping cart contents, or authentication tokens, where quick access is essential. Also, you can use them in caching, like implementing caching layers to boost the performance of applications by storing frequently accessed data in memory for rapid retrieval, reducing the load on the primary database. Also, you can use them in real-time data processing, quickly storing and retrieving data for real-time analytics, event processing pipelines as well, and maybe message queues where low latency is crucial. You can think of Redis, which is a memory data structure that stores anything you need basically, or maybe Amazon DynamoDB, which is a highly scalable and fully managed key value store in the cloud. Next, we have document database. Document databases, they are another branch of NoSQL databases. They are stored data in semi-structured documents, typically using formats like JSON or BSON, for example. This allows for more flexible schema compared to relational databases, making them well suited for evolving data models and scenarios where fast read and writes performance are key. Use case for them, they are heavily used in e-commerce platform like storing product catalogs which diverse and varying attributes with diverse and varying attributes, not which, sorry, handling user reviews with different structures and managing flexible inventory. Content management system as well, you can use them in content management system, ideal for managing articles, user profiles with custom fields and comments where each piece of content can be stored as self-contained document. You can use them also in real-time analytic, and IoT, handling the varied and often unpredictable data structures generated by IoT devices and supporting real-time analysis on this diverse data. Next, we have graph databases. The graph databases are specifically designed to store and query complex networks of interconnected data. They represent data as nodes, which are the entities, and edges, which are the relationships between entities, both of which can have properties. This structure enables efficient traversal, querying, and analysis of highly related data. The use cases of graphs, you can think of social networks, for example, managing user profile and their connections, enabling features like friend recommendations, social graph analysis, and identifying influential users. You can use them in recommendation system, like analyzing customer preferences, product inventories, and purchase histories to generate personalized product or content recommendations based on relationships. You can use them in the knowledge graph, building vast repositories of interconnected data for semantic searches, intelligent information retrieval as well, and sophisticated decision support system. Next, we have wide column store. Wide column stores are NoSQL databases optimized for handling massive amounts of data spread across many machines. They organize data into tables with flexible and dynamic column structures, meaning different rows can have different sets of columns. They excel at high write throughput and real-time data processing. Their eventual consistency model prioritize availability and partition tolerance over strict consistency. The user cases for wide column stores, the first thing I would say is they are great in web analytics and user tracking, capturing and analyzing event in real time, such as website click, user activity logs, and network monitoring data. They also great at real-time analytics like aggregating and analyzing large datasets quickly, making them suitable for dashboards, real-time alerting system, and operational analytics. Next, we have in-memory databases. In-memory databases take a different approach by storing data directly in the computer's main memory instead of the disk, or this is on the disk. So this eliminates the slow disk I/O operations, resulting in extremely fast data processing and low latency. However, this speed comes at a higher cost per gigabyte, and data persistence require specific configuration for that. The use cases for in-memory databases, I guess, in online games like managing real-time user session, game status, and leaderboards, ensuring fast and responsive gameplay experience. Can use them also in high-frequency trading, like enabling a massive number of financial transactions per second with minimal latency, where every millisecond counts. And also, you can use them in caching, like while key value stores can be in memory. Detected in-memory databases are often used for more complex caching scenarios requiring richer data structure. I guess if you want to think about in-memory database example, you can think about like Redis and Memcache, which are popular choices for an in-memory database. Next, we have time series databases. Time series databases are specifically designed for storing, retrieving, and managing timestamp data, where each data point is associated with a specific point in time. They are optimized for the unique characteristics of time series data, such as high write volume, temporal querying, and data retention policies. A common use cases for them, you can use them. You can think about financial trading platforms like tracking stock prices, trade volumes, and market indicators over time for trend analysis and algorithmic trading strategies. You can think about IoT and sensor data management, collecting and analyzing data from sensors and IoT devices, in smart homes, for example, industrial automation, and maybe for environmental monitoring. Also, you can use them in the performance monitoring, like in IT and network infrastructure, and monitoring systems metrics like CPU usage, memory consumptions, and network traffic over time for capacity planning and anomaly detection. Okay, next we have object-oriented databases. Object-oriented databases store and manipulate data as objects, mirroring the concept of object-oriented programming languages. Objects are instead Objects are instances of classes and can encapsulate both data, which are the attributes, and behavior, which are the methods. This can simplify development for applications heavily reliant on OOP and the OOP principles, object-oriented programming principles. The common use cases for that, they are great, like in object-oriented applications, like applications developed using an object-oriented programming languages like Java, C++, or Python that requires a seamless way to persist and retrieve object without complex object relational mapping. They are also great in multimedia databases, storing and managing multimedia items like images, videos, and audio files, where the encapsulation of data and associated operations like play or edit can be beneficial. Um, if you want to think about example of an object-oriented database, I guess there is an ObjectDB and ObjectDB. I guess this is one of the most data object-oriented databases. Next, we have text search database. Text search databases are specialized systems built for efficiently storing, indexing, and retrieving large volumes of unstructured or semi-structured text data. They provide powerful and scalable search capabilities, allowing users to quickly find relevant information within vast collection of documents, web pages, or even logs. A common use cases for them, they are being used in e-commerce, like powering product search within online stores, enabling customers to find products based on descriptions, reviews, and metadata. They are great also in web search, used by search engines like Google, Bing, and DuckDuckGo to index and search the massive amount of content on the internet. They are great in log analysis, like indexing and searching large volumes of application or system logs for troubleshooting, monitoring, and security analysis. I guess if you want to think about that, I guess you can think about Elasticsearch. I guess this is the most famous one. Next, we have spatial databases. Spatial databases are designed to store, manage, and analyze data that represent geographical or spatial information. They handle complex spatial data types like points, lines, and polygons, and provide efficient indexing technique for optimizing spatial queries, crucial for location-based services. A common uses for them, you'll use them like in geographic information systems, mapping, analyzing, and managing geographical data for urban planning, environment management, and emergency response. You could use them in location-based services, providing services based on user location, such as navigation apps and finding nearby points of interest. You can use them also in logistics and transportation, like optimizing route tracking, vehicle movements in real time, and analyze traffic patterns. I guess um, you can use them in PostGIS, which is an extension of PostgreSQL. You can use them this is an example of them. Next, we have blob storage. Blob storage was a binary large object. They are data stores which are designed for storing and retrieving massive amounts of unstructured binary data, such as image, such as audio files, such as videos and documents as well. They prioritize scalability and high availability, durability as well, and cost effectiveness for managing these large complex data objects. You can use them in data and CDNs, which is content delivery networks, which to store storing data and delivering large media files to user globally with high speed and reliability. You can use them in big data storage, like storing vast data sets like log files, sensor data, and scientific data for big data analytics and processing pipelines. You can use them for backup and archival as well, because providing reliable and scalable storage for backup data achieves and basically the archives, not achieves, archives and long-term data retention and at a cost-efficient price. I guess one of the most famous blob storage database are S3, and also um, I guess Google has its own blob storage. I would say in any system design interview, you will have to use a blob storage all the time. Next, we have ledger database. Ledger database is sometimes referred as a blockchain database. They are designed to provide an immutable, append-only record of transactions. Once data is recorded, it cannot be deleted at all, ensuring a verifiable and tamper-evident history of all changes over time, making them ideal for application requiring high trust and transparency. A common use cases for these type of databases, you can think about supply chain management, tracking the movement of goods and materials across a supply chain with transparency and traceability. You can think they are could be used in healthcare systems, like managing patient records, consent forms, and treatment histories with a clear and unchangeable audit trail. You can use them in voting systems, like providing a secure and transparent platform for conducting voting processes, ensuring the integrity of results and preventing manipulating. Next, we have hierarchical databases. Hierarchical databases organize data in tree-like structure, where each record has a single parent but can have multiple children, establishing or like one to many relationships. While popular in early computing, they offer less flexibility for complex, which are many to many relationships compared to other models. Um, a common use cases, I guess they are great in file systems, like the directory structure of a file system is a classic example of hierarchical data organization. And yeah, next we have a vector database. Vector databases are specialized for storing and searching vectors, arrays of numbers representing data in high dimensional spaces. They are optimized for similarity search and nearest neighbors queries, enabling fast retrieval for similar items based on their vector representations, making them crucial for modern machine learning and AI applications, not I applications, AI applications. You can use them in image and video search, like enabling content-based image and video retrievers by storing visual features as high-dimensional vectors and finding similar content. You can use them in recommendation system, like representing users and items as vectors to quickly identify and recommend items similar to users' interests. Also, you can use them in anomaly detection, comparing the vector representation of few points to know normal samples to identify outliers based on the dissimilarity. Okay. Lastly, it was a long video. Lastly, we have the embedded databases, which the embedded databases are designed to be tightly integrated directly into software applications. Unlike client server models, they run as part of the application process itself, offering fast data access, a small footprint, and simplified deployment, particularly useful in resource constrained environments. I guess the use case of them, it will be gaming, like saving game status, player progress, and configuration settings directly within the game application itself. You can think about using them in desktop applications like storing configuration settings, user preferences, and application specified data locally on a user's machine. So, as you can see, the world of databases is incredibly diverse. There is no one size fits all solutions. The best choice depends entirely on your specific usage, the nature of your data, your scalability requirements, and your budget. Understanding these different types and their strength is a fundamental skill for any aspiring system designer. So that's it for this video, and see you in future videos.